Okay, in this video I'm going to walk through the exam review or the practice exam for physics exam number 5. So if you recall, exam number 5 actually covers several chapters from our textbook, and in this review specifically we're going to cover chapters 11 through 14. So here we go, let's take a look. If you recall, we started this unit with chapter 11, where we were talking about statics in fluids, or fluid statics. And question number 1 is precisely that: which has a greater buoyant force on it, a 25 cubic centimeter piece of wood floating with part of its volume above the water, or a 25 cubic centimeter piece of submerged iron? Now, at first, when I read this, I missed the fact that the wood is floating with part of its volume above the water, and so it would be easy to say at first that the two have equal buoyant forces. Recall that a buoyant force is the force upward, and that's equivalent to the density of the fluid times the volume of the fluid displaced times the gravitational constant. So the buoyancy force is essentially mass times gravity of the water that's being displaced in this case. So if both of these were underwater, then they would have the same buoyant force. However, since the block of wood is floating above the water, only a portion of it is displacing water itself. So we would say that part B is correct. The iron actually has a greater buoyant force pushing up on it because it is displacing more water. So in number 2, we're being asked if the specific gravity of some material is 2.9, what is the mass of half of a cubic meter of this material? Well, for our points of discussion, we said that specific gravity is the density of an object compared to the density of water. So the density of any object is its mass divided by volume, and the density of water for our purposes has been reported as 1,000. So if we have m divided by 0.5 cubic meters divided by 1,000, when we do the math to isolate that, we end up finding that the mass of the object is 1,450 kilograms. And moving on to number 3 here. Oops. In this case, we're dealing with a box that has a mass of 5 kilograms, and the bottom of the box measures basically 100 square centimeters, and we would like to find the pressure that the box exerts on the tabletop. So this doesn't really mention anything about atmospheric pressure included in this problem. We're literally worried just about how much pressure is being exerted from the box onto the tabletop. So I think this was on page 1 of our notes even. The formula for pressure is equal to the force applied divided by area, and the force applied in this case is the mass of the box times the gravitational constant divided by the area. Now 10 centimeters times 10 centimeters is 100 square centimeters, but we should convert that into standard units to make our math a little bit more meaningful. And so if we're using 0.01 square meters with 5 kilograms of mass and our gravitational constant, 4905, or approximately 5,000 pascals of pressure, is what's experienced in this situation. So now moving on to number 4. Here's where we transition out of fluid statics and into fluid dynamics. So this was chapter 12 content. Water's flowing through a pipe that has a diameter of 8 centimeters with a speed of 10 meters per second. It then enters a small pipe of diameter 3 centimeters. What's the speed of the water as it flows through the smaller pipe? Well, let's not forget that my recommendation for completing any of these problems is to report your work in standard units. So immediately I'm converting diameters into a radius, because I'm going to use radius to compute area in just a second. But also, instead of a length of centimeters, we're going to call that a length of meters. So the radius of this pipe at the beginning is 0.04 meters, and the radius of the pipe at the end is 0.015 meters. And so the nice thing is, due to the equation of continuity, the product of the area times velocity, or in other words, the flow rate, at one position of the pipe is equivalent to the flow rate in another position of the pipe. So in this case, we're looking for the velocity as it's flowing through the smaller pipe, and I noted that as V2. So in order to isolate V2, we simply divided both sides by A2, and we substituted the necessary values to compute the area at the beginning and at the end, as well as the velocity along the way. Now, velocity was already in a measurement of meters per second, so there was no conversion necessary there. And the pi values canceled, and after entering this into the calculator, it appears that 71 meters per second is the appropriate result for question number 4. With number 5, we have a physics professor that weighs, or that has a mass of 73.5 kilograms. The bed consists of a large number of evenly spaced sharp nails. We have approximately 1,900 nails that are making contact with the professor's body. So this actually falls out of the fluid statics portion of the unit and actually goes back into well, I was going to say a pressure situation, but we don't really know the area of the nails that are being applied here. We know that there are 1,900 nails, so in a sense that kind of acts as an area value. So even though we have a large force, the mass of the professor times the acceleration due to gravity, that could say g instead of a here, we have a large force that's being applied, and that force is being divided over 1,900 points. So when I wrote down Fn, what I'm indicating here is that the force of the nails, the 1,900 nails, is equal, or force on each nail individually, I should say, is the total force of the professor due to gravity divided over the 1,900 nails. And so each nail has to support 0.3795 newtons of force, otherwise the professor would be moving still, but they said that he's laying down, and I assume that he's resting still, or she's resting still. So again, in a sense, you can think of this as a pressure problem in that we have a force divided by an area, while specifically we don't have the actual area of contact here with those nails, but the 1,900 nails acts as a method to distribute the force over all of those components. So if we knew the area of the tip of each nail and we have the force applied at that position, we can determine the pressure and then run some investigations to determine whether or not the pressure would be sufficient to pierce the skin of the professor, which we certainly would hope not to be the case. So interesting question. At first I was a little confused because it didn't seem like it fit our chapters very well, but in actuality I think it's a close relation after all. Okay, so maybe I was mistaken in thinking that this would be a nice progression of questions from chapter 11 to 12 and so on. Because as I look now at number 6, which one of the following statements considering buoyant force is true? Well, again, we're back into fluid statics here. Well, recall that the force due to buoyancy, or the buoyant force acting on an object submerged in a fluid, is the density of the fluid times the volume of the fluid displaced times the gravitational constant. So if we're considering that definition, and I'll just highlight this one here, you'll notice that the mass of the object has no play on this computation. So I know that A is no good. Mass is not going to affect this. And same thing with weight. If mass of the object doesn't affect the buoyant force, then neither will weight. Now, weight is a little bit closer here in that we're multiplying some mass times gravity, but again, it's not the mass of the object that we're concerned with, it's the mass of the fluid that's being displaced. So on two accounts, I would say that A and B are no good. We're not worried about the mass or the weight per se, and it's definitely not of the object itself. To say that C, the buoyant force, is independent of the density of the fluid, well, clearly that's not true, because you can see right here the buoyant force is absolutely dependent upon the density of the fluid. We need to know exactly what that is because that's part of our computation. And then finally, buoyant force depends on the volume of the liquid displaced. And certainly that's what we're pointing to right here. The volume of the liquid that's being pushed out of the way by the object that's submerged. So I like D as an answer here. All right, so question number 7 again is another theory style question. Which of the following statements about a completely enclosed fluid is true? Any change in the applied pressure of the fluid produces a change in the pressure that depends on the direction. Now, that's may not be worded very clearly, but I'll just try to make my argument here. If I had an object inside this enclosure and I apply a pressure from this direction and consider how the pressure on that object would be affected, and then if I were to apply a pressure from this direction, consider how the pressure on this object would be changed. Well, it doesn't matter which direction the pressure is being applied, the pressure change in this enclosed situation is going to be uniform throughout. So it doesn't really depend on the direction at which some sort of applied pressure is being brought into that system. So I don't like the answer A. To say that the pressure at all points within the fluid is independent of any pressure applied to it, well, that's not true. If this is an enclosed system and we apply some pressure to it, well, the pressure throughout the system is going to increase. And that's exactly what we're saying here in part C. A change in applied pressure produces an equal change at all points within the fluid, so that's true. And then we don't really have to read through the rest. However, part E was kind of interesting to me because it says the pressure in the fluid is the same at all points within the fluid. And again, this would only be true in a uniformly shaped enclosure. And actually, the more I think about that too, this I think is more of an illustration of fluid that's actually flowing through the system, and that's not really happening here. So there's a higher pressure when the fluid is moving more slowly or in a smaller confined space. There's a lower pressure where the fluid is moving faster. So I think I may have said that backwards. Where the fluid's moving faster, we have the lower pressure, so it's moving faster down here in this narrow chamber. It'd be moving slower here in this wider chamber, and it would have a higher pressure. But then the other thing that I'm thinking of right here too is that the depth of the fluid makes a difference. The pressure would be greater at the bottom than it is at the top. So to say that the pressure in the fluid is the same at all points within the fluid, that's just wrong on a couple different accounts. So I still think that C is a good answer here. If we increase the pressure to that system, then the pressure will increase by that amount throughout the entire system. And question number 8 is actually an extension of that problem. It really does revolve around Pascal's principle that if we have two circular pistons with different radii and a force was applied on the smaller piston, how big of an output force would be achieved? Well, we need to remind ourselves that the pressure on one side of the system has to be equal to the pressure on the other, and pressure is the force divided by the area. So pardon the typing here, but hopefully you can follow along with this. And if F1 divided by A1 is equal to F2 divided by A2, then you can see where this is coming into play. If I multiply both sides by A1, I now have F2 times A1 over A2. And we can then isolate F2 in this case. Now I labeled F1 as the input force and R1 as the input piston diameter or radius. So my subscripts of 1 are the input values, and we're trying to find the output value. So that's what I'm labeling as F2. So the force being 20 newtons, the area of a circle being used here. When we substitute all the known quantities, we end up with 4,500 newtons. And a clear benefit to the power of hydraulics. Now with number 9, again, we have to be careful with the way we read this problem and interpret it. A horizontal piping system delivers a constant flow of water. Now that's important that it's a constant flow. This is not an enclosed system. It's constructed from pipes with different diameters that are shown, and at which of the labeled points is the pipe under the greatest pressure. So if we're viewing from above the pipe, now this is something that we can easily overlook here. Some people will look at this diagram and think that this is a side view of the system where point A is at a low point and point C and D are at a high point. And so that could be a bit misleading. We're looking over top of this and assuming that the water is essentially a horizontal flowing system. And so all that we need to recall here is that the lowest pressure occurs, the lowest pressure occurs where velocity is the greatest, but we're trying to answer where is the highest pressure going to be. Well, the highest pressure occurs when the velocity is the lowest, and the lowest velocity occurs when the cross-sectional area is the greatest. So the water would be moving the slowest at A and the fastest at either B or D. So the high pressure points are here at B and D. The low pressure points are at B and D. That's where the water is moving the fastest. And the high pressure point here, where the water is moving the slowest, is at A. Now, if this was a closed system, or if this was the side view, then we'd worry about pressure on account of the depth of the fluid, adding a pressure to it. And so I would again say that A has the highest pressure, but in that case it's because it's the lowest point in the system. Okay, so now I think it's safe to say we're done with the fluid chapters. So chapter 11 and 12 are now done. Now we can look at chapters 13 and 14 for heat and temperature change. So if absolute zero on the Celsius temperature scale is negative 273.15 Celsius, what's the absolute zero on the Fahrenheit scale? Well, that's easy. We'll just use the Fahrenheit conversion rule. We'll substitute negative 273 in place of the temperature in Celsius and find that negative 459.67 is the absolute zero for degrees in Fahrenheit. Number 11, we've got another thought experiment that's happening here. A steel plate has a hole in it with a diameter that's exactly 1 centimeter, and this is when the temperature of the plate's at 20 degrees Celsius. A steel ring has an inner diameter of exactly 1 centimeter at 20 degrees Celsius as well. So this is a crude drawing here. This is meant to be a big plate with a hole that has a diameter of 1 centimeter in it, and this is supposed to be a ring that also has a diameter of 1 centimeter inside of it. And so the plate and the ring are both heated to 100 degrees Celsius. We want to know which is true. Well, the thought might be, well, the plate's going to change size at a different rate than the ring because it has a larger mass, or maybe vice versa, you're thinking it. But in actuality, you just have to recall the change in area formula based on temperature. And we call that thermal expansion. So we had a rule that said the change in area is equal to gamma times the initial area times the change in temperature, where gamma is the coefficient of expansion, in this case area expansion. Now, if these two objects are made from the same material, the same type of steel, the gamma value is the same in both situations, or in both objects. The initial area is the same in both because we're talking about a punch out that's 1 centimeter in diameter. So that's the component that we're worried about the change in. And then the change in temperature is the same. So if we're saying that gamma, initial area, and the change in temperature are all the same, then the change in area is going to have to be the same as well. So part C would be the correct answer here. The hole in the plate and the hole in the ring get larger because of the temperature increase, and they get larger at the same rate. So clearly A, D, and E don't work here. B is a bit tempting, but we do have to recognize that the area is exactly the same regardless of the surrounding material. They both change at the same rate. So C is the best answer here. For number 12, a tanker ship is filled with this much gasoline, and notice that it is in cubic meters already. That's a lot of gasoline. and that was filled when the temperature was 17.2 degrees Celsius. Upon arrival in New York City, the temperature has dropped, and the coefficient of volume expansion for gasoline is given to us by this number here. How much has the volume of the gasoline decreased? Well, this one's pretty straightforward. The change in volume is equal to beta, the volume coefficient or expansion coefficient for gasoline, times the initial volume times the change in temperature. All of that information was provided. And note here that the temperature dropped, so 1.3 minus 17.2 is a negative number. We would expect that gasoline to take up 3,000 cubic meters less than what it was when it began its journey. For number 13, we start talking a little bit about calorimetry here and heat transfer. So water loses, or water at 0 degrees Celsius loses 1,140 calories worth of heat. So a couple things that are working here. Number one, we have water at 0 degrees Celsius. So it's in that latent heat portion of its phase change. So it can be losing heat here. Heat would be the energy transferring out of the material, but the temperature of the material is not changing while the phase change is happening. So if only 1,140 calories has moved out of this material, then we can compute that by using our heat flow formula for latent heat here. So we've got the amount of heat that's been transferred is equal to the mass times the coefficient, I should say constant of fusion for water. So the heat that's been lost is negative 1,140 calories, and the coefficient or the constant here was 79.7. So when we divide those two, we end up with negative 14.3 grams. And I was real hesitant at the very end there because I realized I did the math without standard units here, but that's okay because the constant for fusion of water was actually given to us in calories per gram. Our heat transfer was measured in calories, so the units agreed with one another. I recognized that the solution at the end would be a measurement in grams, which is what we were after anyway. Normally, again, I would argue to convert all of your units into standard units first and then perform the math, but in this case, it worked out nicely for us. Now, number 14, a metal sphere that weighs 0.33 kilograms has a specific heat of 649 joules per kilogram degrees Celsius, and it's heated from 21 to 163 degrees Celsius. How much heat energy is required? Well, this is pretty straightforward. Again, the heat energy, the flow of heat in this case, is mass times the constant times the change in temperature. That was all provided to us. In fact, the change of these two temperatures was pretty straightforward, and I just reported that as 142. So we ended up with 30,000 joules of heat. Just note that our answer was kilojoules, so we got that by simply moving this decimal 3 places to the left, or dividing by 1,000. Okay, number 15 is really a vocabulary question. When you put ice in a glass of warm tea, what happens? Does the cold flow from the ice cube to the tea? Does the cold flow from the ice cube into the tea? And heat flows from the tea into the ice cube at the same time? Well, let's just be real clear about this. A and B are false because cold does not flow. It's the heat that flows. The heat is the measurement of the energy transferred from a high temperature to a low temperature. So we would never say that cold flows. We say that heat flows and replaces the cold, air quotes, cold here. We would not say that neither heat nor cold flows, only temperature flows. Well, that's not really correct. Temperature changes, but the measurement of the energy for that temperature change is heat. So part C is the appropriate answer here. Heat flows from the tea into the ice cube and that energy will ultimately melt the ice cube. Okay, so for the last 3 or 4 questions, I think, yeah, we've just got 3 in the review here. I had mentioned in class last week that it's worth your while to reread the notes for chapter 14, especially pages 6 through 9 on energy transfer. That'll help you with these last 3 questions. So I'll try to add my 2 cents here. I know the video is getting kind of long, but we should be wrapped up in just a few more minutes. So I'm going to bring in the notes. Let's see if I can get this to show up on the screen at the same time. Here we are, page 6 in our Unit 5 notes on energy transfer. Question 16 says to discuss or identify the transfer of the heat by convection. And convection is a measurement of fluid movement. So conduction is the first type of energy transfer that was covered in the notes. And that's where we have direct physical contact with one object and another. We've got a heat source here at T2 touching this bar in the center, and it's moving its heat or transfer of heat through that bar directly. Now, if we were to scroll forward and find discussion on convection, it's a small section here, but remember, we're trying to imply here that convection is the heat transferred by the flow of matter, and we usually discuss this in terms of fluids, so air or I'm sorry, gases or liquids, as the objects start flowing with one another, we'll start to see the energy transfer. So with that in mind, and this convection status, we were talking about the hot air balloon or the heating of a pot of water without actually touching it. You'll sometimes see these cycles drawn. Sorry, I'm trying to do this with my mouse here, where temperature currents are kind of cycling like this. That agitation, that shaking of the heat currents, that's how objects are transferring heat in this case. So that movement as such does not occur in metals or in a vacuum or in solids. And it can't be done without the presence of matter, even though we may think of gases as an empty object. There is matter there. So the liquid or a gas, the fluid, if you will, is required in order for convection to occur. The only way that heat will transfer by convection is with the movement of the matter itself, the liquid or the gas actually sloshing around. Now with number 17, there's a lot going on here. This is an example of conductivity or heat by conduction. So for that, we want to refer to that section in our notes. That was back on page 6, if I'm not mistaken. Yeah, here we are. When we first started talking about conduction, there was a formula here. And so it's the flow of heat with some component of time, and the time value is going to be seconds here. K is a constant or coefficient for conductivity of a material. Now, with that one, again, we'd have to look up our data in our tables, and that was table 14.3 in our textbook. So do make sure that you're referencing that for this problem. But the long and short of it in this particular case, if this is our formula, Q divided by T equals K times the area times the temperature hot minus temperature cold divided by the distance that the heat has to travel, well, most of that is actually provided here in this problem. And the question ends up being how much heat is transferred in 1 hour. So we have our hot side temperature, 20 degrees, our cold side temperature, 5.2. The distance that it has to travel from one side of the wall to the other is 1/2 meter. The conductivity of granite is given to us. The time is given to us. So all this information is given to us. We can certainly just start plugging it in. Take note, though, that time was provided in hours, so the t value that we want to use is seconds. So I made that quick conversion. That's a mental conversion you should be aware of. We've got a distance in meters, temperature in Celsius, which is good. Square meter is the area of the granite wall that we're dealing with. So yeah, everything can be substituted straight in here and calculated for Q. Now, just to make sure that my units worked out, I did jot those down off to the right-hand side. 2.1 was a unit of watts per meter degree Celsius. 3,600 seconds was our unit of time. 1 was 1 square meter of material. So for both of those, I just wrote those as a fraction over 1 to help see where components would cancel. And then at the end, we had the temperature change divided by the distance, so degrees Celsius divided by meters. And so the meters squared from the area component canceled each of the meters over here. Celsius canceled with Celsius. And so what we actually calculated was 223,000 watt seconds. And if we take this one step further and recognize that a watt is the measurement of joules per second, energy per unit of time, then the seconds do cancel and we are indeed left with joules. Now, at first glance, that might be a problem because all of our answer choices are joules per meter squared. One thing that we can't forget about, though, is that this was the amount of energy that flows through precisely 1 square meter of the granite wall. So by design of the problem, it ended up working out pretty nicely for us. Now, as a side note, I went and wrote this down after I did my math earlier. If we took the original formula and divided both sides by A and multiplied both sides by T, an alternate form of the equation would look like this, where we have our heat flow per unit of area, and that's simply equal to the K times T times temperature divided by D, which also would have resulted in the exact same result. And again, we would have obtained our joules per square meter as our unit of measure there too. So for 17, I like A as an answer. Just read through everything carefully, identify the proper components, and substitute in the heat transfer equation that's provided to us. And this is for conductivity, heat transfer through contact. This last example is heat transfer through radiation. So this is not convection. It's not a transfer by non-contact via convection. This is actually radiant energy from a heat source. And for that, we have another set of rules to follow. So we've got to scroll down. I think this is way at the end here. Yep, here's our radiation formula. This is the Stefan-Boltzmann law. Now, what's kind of interesting about this is that the E value and the lowercase sigma value have to be provided. Now, the lowercase sigma is truly a constant. It remains consistent regardless of the material that we're working with. So here's the value for the sigma, the Stefan-Boltzmann constant, and its unit here as well. Now, notice that this constant is measured with a unit that contains temperature in Kelvin. So when we use this formula, Q over T equals E sigma times alpha times temperature, the temperature that we use here does need to be in Kelvin. So there may be a conversion necessary for that. And I think what's being noted here is that the temperature of the object and the temperature of the environment in which that object sits, there's a difference between those two, and we would actually use that difference in temperature in the computation itself. Now, in our example over here, we don't have temperature from the environment contributing to the absorption rates here, so we actually won't be doing that. We're just going to be using the original formula here. So QT equals E sigma A times T to the 4th power. So as we look at number 18, the rate of energy output via radiation of a star, whose radius is supplied. Now, if we have the radius, we can calculate the surface area. That does say A for area, but we got to recognize that this is a surface area, three-dimensional object. The temperature is 7,100 Kelvin, and we can assume that the star is perfectly emissive. And according to our notes, something that's a perfect emitter of energy has an E value of 1, and I think there's a typo here. The perfect emitter radiates energy. So the perfect emitter is a radiator of energy. On the other scale, on the other side of the scale, if the emissivity rate of 0 means that it doesn't radiate any objects whatsoever, it absorbs all of the energy. So if it can't radiate, it can only absorb energy. That would have an emissivity of 0. So anyway, in this case, we have perfect emissivity. It's perfectly emissive, so the E value is going to be 1. So as we substitute our values here, our energy transfer divided by unit of time is equal to E times sigma times A times T to the 4th. We are reminded that the surface area of a sphere is 4 pi r squared. So even though we were only supplied with the radius here, we had to calculate the total area, area being the result of this small computation. So I brought this whole expression into the calculator and let it do its thing. And again, we're taking note of the units here. The unit of our constant was watt per meter squared Kelvin to the 4th power. So we had an area measurement of meter squared, and then our temperature of 7100 Kelvin raised to the 4th power is Kelvin to the 4th power. We got our units to cancel. We were left with 1.41 times 10 to the 27th watts. Watt is a measurement of joules per second. So to note heat transfer per unit of time, that's meaningful to us to say that the energy transfer is done in watts. So that ended up being quite a lengthy video. I'm kind of glad I ended up doing this in one setting though, so you don't have to go finding multiple videos and you can just scrub forward and backward through each of the questions that you have. If you do have other questions on this review or on anything else as you prepare for the Unit 5 exam, please reach out to me. I should be available throughout the week. If not in person, then by email or by messages through Schoology. Thanks a lot, everybody.